Hello, in today's video we're going to be discussing section 7.6 on exponential and logarithmic equations. The first thing I want to talk about is solving exponential equations by using like bases. If we have the same base on both the left and the right hand side of our equations, then that tells us our exponents must be equal. So for example, if I have a base of 5 to the power of 3 on the left, and that's equal to a base of 5 on the right as well to the power of x, well, then we can solve for x by knowing our exponents must be equal to one another. So x has to be 3. The only value I can replace x with in order for the left and the right hand side to be equal is a 3. So what we can do with that idea is then take this into more advanced concepts. If I have, for example, 2 to the power of 5x minus 1 is equal to 2 to the power of 3x. I can say I have the same bases, so then my exponents must be equal, giving me the equation 5x plus 1 has to equal 3x. Those exponents must be equal to one another. We can take this one step further and say I have a base of 6 to the power of 5x plus 2 is equal to 36. Now these do not have the same base, however it is possible to take 36 and write it as 6 to the power of 2. So now the base on the left and the base on the right are equivalent, so I can write the equation 5x plus 2 is equal to 2 because my exponents must be equal when my bases are equal. So in example 7.6.1, I'm going to go ahead and use that strategy that I showed you last. I want my bases to be the same so that I can let my exponents be equal to one another. So on the left, my base is as simple as I can get it, so I'm going to focus on manipulating that right-hand side. I do see divided by 3, and I do know that dividing means I can write this as multiplication with a negative power. So all I did is I took that divide by 3 and I rewrote it as 3 to the negative first power. From here, I can then add my exponents, since we are multiplying the bases, to get 3 to the power of 2x minus 1. Well, now that I have the same base on the left and the right-hand side, I can write the equation for x minus 7 is equal to 2x minus 1 because I know that my exponents must be equal since my bases are the same. So 2x minus 7 is equal to negative 1. Adding 7 to both sides, 2x equals 6, so x is equal to 3. All right, your turn. Pause the video and try out these next couple on your own. 256 I can rewrite as 4 to the 4th power, which is equal to 4 to the x minus 5 power. From there, my exponents must be equal, so I have the equation 4 equals x minus 5, so x must be 9. In 7.6.3, I want to write both the left and the right-hand side with a common base. So my goal is to rewrite 8 and 16 so that they have the same base. Well, they are both powers of 2, so I can rewrite 8 as 2 to the 3rd power and 16 as 2 to the 4th power. Now I have the same base on both sides, so I use properties of exponents and simplify. So 2 to the power of 3 times x plus 2 and 2 to the power of 4 times x plus 1. Since my bases are the same, I now know that my exponents must be equal as well, so I have the equation 3x plus 2 is equal to 4x plus 1. So 3x plus 6 is equal to 4x plus 4. And solving, 6 is equal to x plus 4, and 2 is equal to x, or x is 2. We can also use logarithms to solve exponential equations when our bases are a little bit trickier to work with. So log is a function that we can apply just like the operation of multiplying, dividing, adding, or subtracting. We can apply this operation to both sides of our equation. The reason I'm going to do that is because log helps me isolate exponents. And since my variables here are in exponents, I'm going to go ahead and free them up by taking the log of both sides. Just like, again, you would multiply, divide, add, or subtract, you can apply the function of log to both sides. Now, in a previous lesson, we discussed how I can move that exponent as a coefficient on my log to get x plus 2 times the log of 5 is equal to x times the log of 4. Now I will go ahead and distribute my log because my goal is to isolate x, so I want to make sure that I can free up that x to combine those like terms together. So now I can move the x from the left by subtracting the entire x term, which is x log 5, from the left and the right-hand side. So I've got 2 log 5 is equal to x log 4 minus x log 5. Should be multiplication, x times log 5. Which allows me to then factor out that GCF of x. Factoring out the GCF leaves me with log of 4 minus log of 5. And since I have the same base, the base of these logs is each 10, I can combine this by taking the quotient of 4 and 5 to get log of 4/5, numerator, and then minus my denominator, or numerator over denominator. To isolate x then, I just need to divide by that log of 4/5 on both sides of my equation. And we are done. X is going to equal 2 times the log of 5 over the log of 4/5. All right, go ahead and take a moment, pause the video, and practice these next couple on your own. My first step is going to be to isolate that exponential component. So I divide by 20 to get 5 is equal to e to the power of 2t. Now I want to isolate my exponent, which tells me that I'm going to bring in logs. Since natural log has a base of e, I'm going to use natural log on both the left and the right-hand side. This allows me to go ahead and move that 2t to the front, so natural log of 5 equals 2t times the natural log of e. Now as a side note, natural log has a base of e. So what we are saying when I have natural log base e of e is I want to know what power I put on e to get e. So really what we're saying is I have e, I want to raise it to some power to get e, which means that that exponent has to be a 1. So if I go ahead and back up here, log base e of e has to equal 1. So then this whole component here is just 1. So natural log of 5 equals 2t times 1, which is just 2t. So then I can solve for t by dividing by 2. 1/2 times the natural log of 5 is equal to t. And we can condense this further by putting our 1/2 back as an exponent. So t is the natural log of 5 to the 1/2. Similarly in 7/6, I'm going to isolate the exponential component by first subtracting 5 on both sides, and then dividing by 4. That leaves me with e to the power of 2x equals 7/4. And since I'm trying to isolate the exponent, I will use logs. Since I have a base of e, I want to use a natural log. Pretty much anytime you see e, that should ring a bell that you're going to be bringing in a natural log. So I move that exponent out to the front. And ln of e, or log base e of e, is just 1, as we talked about before. So 2x is natural log of 7/4. Divide by 2. X is equal to 1/2 times the natural log of 7/4. And we can go ahead and put that exponent back on. X is the natural log of 7/4 to the 1/2. Or in other words, 1/2 does mean square root. And I can square root that denominator to give me the natural log of the square root of 7 over 2. So I just simplified all the way down. I moved my exponent back. 1/2 actually means square root. Square root of 7 is not an integer, but the square root of 4 I was able to simplify down to 2. In example 767, I actually see that there is going to be a quadratic form here. And the reason I see that is because I have something with a power of 2, and then that same thing repeated, but with no power of 2. So what I'm going to do is rewrite this so that it takes the form of a quadratic. So I have e to the x, I'm going to raise that to the power of 2, minus e to the x, and then I will subtract my 56 over. And this will equal 0. So what I can do from here is say I'm going to let e to the x be represented by maybe a. So then I have e to the x, or a to the second power, minus e to the x, which is a, minus 56 is equal to 0. So this quadratic is much more friendly for me to work with. I can factor to get a minus 8 times a plus 7 is equal to 0. So a has to equal 8, or a is negative 7. Now a was just a placeholder, so I go back in and I put in my e to the x to get e to the x is 8, or e to the x is negative 7. And this is an equation that I now need to solve. So I take the natural log of both sides and move my exponent out to the front. So x times the natural log of e is equal to the natural log of 8. Natural log of e is just 1. So x is equal to the natural log of 8. Now here I have a little bit of a problem, because e to an exponent is a negative number, but that doesn't make any sense because e is positive. So if I have a positive number and I'm raising it to an exponent, that exponent can be as negative as we want. We are never going to have a negative answer as our output. So this is going to be a problem. You may remember when we went to graph our exponential functions, how we had a horizontal asymptote at the x-axis, because no matter how small our x values got, we never touched or crossed that x-axis. So e to the power of x is negative 7, does not give us a solution, so our only solution here is natural log of 8. We can also use the definition of logs to solve logarithmic equations. First thing I'm going to do is isolate my log function. So I'm just going to undo everything that I can to try and get x by itself. I see multiplication, so I'll go ahead and divide by 2, and I have now isolated my log function. Now my variable is inside the argument of that log, so in order to get it out to where I can work with it, I'm going to take this out of log form. So 10 to the power of 2 is going to equal x plus 1. So 10 squared equals x plus 1. 100 is equal to x plus 1, which means that x is 99. So if you are trying to solve for an exponent, so for example 10 to the power of x equals 1,000, we want to use logs. If we are trying to solve for the argument, so in this case for the example, log of x plus 1, we want to go out of logs and into exponents. So use the form that you have and manipulate it in order to isolate your variable. All right, I'd like for you to pause the video and try this one here on your own. One of the most important keys here is that we do need to contract or condense our logs first. So on that left-hand side, I do see that I have addition between logs that have the same base, which means I can multiply those arguments together. And I'll simplify to get 6x squared plus 15x is equal to 2. Now my variable is inside the log, so I'm going to take this out of log form by getting 3 to the power of 2 is equal to 6x squared plus 15x. This is now a quadratic that I can factor and solve. So I've factored, and then solving, I've got x is 1/2 and x is negative 3. And it would be wise to go back here and check your solution. All right, one more for you to practice. We will need to condense our logs here. So pause the video and I will show you the solution momentarily. Condensing my logs, I have the same base, which tells me that those arguments must be equal, so I have a solution of x is 10. That brings us to the end today. Thanks so much for watching and have a great day.